In this final video, we're going to go through and work through an example together, and then we'll summarize everything we've learned about drag. In this example problem, the profile of a typical 1,500 kilogram passenger car, as seen from the front, can be approximated with a rectangle that is 1.6 meters wide and 1.4 meters high. Aerodynamic body shaping happens to give a drag coefficient of 0.35 for this particular vehicle. At what speed does the magnitude of the drag force equal that of the rolling friction? So typo there, that should be force. Apologize for that. Actually, I think it should be equal. All right, so we already have a free body diagram, so we'll start here. Now, our sum of forces in the y direction we can see are the normal force minus the gravitational force. And since the car is not moving, has no velocity, or has no acceleration in the y direction, it's just driving along the road, we know that that's going to be 0. So our normal force equals the force of gravity, which is mg. So now we'll do the same thing for the forces in the x direction. So the sum of forces in the x direction will be the propulsion force minus the drag force minus the force of rolling friction. Now all of this will be equal to mass times the acceleration in the x direction. And that acceleration is not constant because the drag force changes as the speed of the car changes. And the speed of the car changes anytime that there is an acceleration. So what we want here is to figure out when my drag force is going to be equal to the force of the rolling friction. So it actually doesn't matter what this propulsion force happens to be. So if we plug in for each of these forces, our simple model for the drag force, and for the rolling friction, we need the coefficient of rolling friction, and that's going to be multiplied by the normal force, which we have calculated in this instance to be mg. Remember, it's not always going to be mg, so make sure you actually solve for that normal force before you go through and do anything like that. Now, if we think about our knowns at this point, we have our cross-sectional area, we have the mass of our car, we have a drag coefficient. We know what sort of values to use for rho. We said we should always be using 1.3 kilograms per meter cubed unless we're told otherwise. So the only other thing that we don't know in this problem is the speed, which we're going to go through and solve, and the coefficient of rolling friction. So this car is driving down the road. So if we go look up in our book, or if you look in one of the earlier videos, we can see that the coefficient of rolling friction for rubber on concrete, which would make sense for rubber tires driving on a concrete road, is 0.02. So that's what we'll go through and use for the coefficient of rolling friction. And then I forgot to mention we also have g, but hopefully by now we've gotten pretty used to knowing that that's going to be 9.80 meters per second squared, our free fall acceleration. So if we go through and solve this equation for our speed, we'll find it is going to be the square root of 2 times the coefficient of rolling friction times mg divided by our drag coefficient, rho, and the cross-sectional area. We can plug in all of these numbers. square root everything. And we'll find the answer is 24 meters per second. So 24 meters per second is roughly 50 miles per hour. That's a reasonable freeway speed. So what that tells us is that because at lower speeds, the rolling friction force is what's going to be higher, because our drag force, again, being speed dependent, will be smaller at that point, and our rolling friction force is not going to change. That at low speeds, we can reasonably ignore air resistance. So under 30 or 40 miles per hour, when you're driving down the road, air resistance is not really doing much to slow your car down. It's mostly the rolling friction between the tires and the road. But once you get up to, say, 50 miles per hour or so, the air resistance becomes a measurable force that can no longer be ignored. So if you have calculations that ignore the drag force at speeds greater than 50 miles per hour, those calculations will be inaccurate, because the drag force takes over at higher speeds, approximately the 50 miles per hour that we calculated here. So in summary, we've learned that the drag force is complex, but we can model it in a simple manner for cases where we have objects that are people scale objects, from a few millimeters, which might be the depth of your fingernail, to objects that are as big as a car, for example, which people ride in. These objects can be moving at people speeds. So speeds at which you walk, or speeds at which airplanes fly. So as long as it's something that people might reasonably do with objects in their everyday life that aren't too extreme, so no bullets, then we can use this simple model shown over here to model what that drag force is. And again, the direction of the drag force is always opposite the motion. It's a resistive force. It resists motion, constantly trying to slow it down. In this simple model, the drag force scales with speed squared. The drag force is not a constant force, so we cannot use our constant acceleration kinematics unless we have two particular situations which result in what's known as either terminal or maximum speed. And those only will happen when acceleration equals 0. And if you have 0 acceleration, it means you're working in a constant velocity scenario, so kinematics end up not being very useful to begin with. Finally, when modeling these objects, we can often use simple shapes to model the cross-sectional areas. In the example problem we just did, we modeled a car using a rectangular area. So either you will be told or given a hint in a problem as to what sort of shape you should be using for the cross-sectional area, or you'll just be straight up given it. And the same goes for the drag coefficient. You will either be given that in the problem, you'll be able to either look it up in a table, or you'll be able to go through and actually be solving it for that particular problem.